Okay, so this lesson is on section 6.4, which covers the Runge-Kutta methods. The Runge-Kutta methods are actually a family of methods that includes Euler method and the explicit trapezoid method that we've already looked at. Specifically, we're going to look at the most famous Runge-Kutta method, which is the fourth order Runge-Kutta method, or RK4. So the formula for W sub I plus 1 you see written here. It's W sub I plus H over 6 times a sum of things involving S1, S2, S3, and S4. And so now I'm going to write down what those things are. Okay, the S's are all related to f of ty, or an actual evaluations of f of ty. So specifically, S1, so S1 is equal to, it's the function evaluated at t sub I, W sub I. And S2 is equal to the function evaluated at t sub I plus h over 2. And then the y component is W sub I plus h over 2 S1. And S sub 3 is equal to f of t sub I plus h over 2 W sub I plus h over 2 times S2. And S sub 4, now we're evaluating the function. So you can see that S1, we're evaluating the function at a left endpoint. S2 and S3, we're evaluating the function at a midpoint. S4, we are evaluating the function at the right endpoint. So it's f of t sub I plus h W sub I plus h S sub 3. Okay, so this is RK4. There are 4 function evaluations. So you can think if we want to compare this to Euler method and explicit trapezoid method, well, there's 4 times as much work at each step comparing Runge-Kutta fourth order to Euler method, and there's twice as much work comparing Runge-Kutta fourth order method to explicit trapezoid method. Okay, and then after we do our first example, we'll try to make a comparison of how much extra work is involved and how much extra accuracy we obtain with this higher order method. Okay. So the example we'll look at. So the initial value problem we will consider is y prime equal to y minus t squared plus 1. This is the differential equation. And the initial condition is y of 0 equals 0.5. So we know that w sub 0 equals 0.5. Of course, t sub 0 equals 0. And so we're going to solve using Runge-Kutta fourth order, I'll just abbreviate RK4, with h equal to 0.2. We're just going to do one step. So S1 is equal to f evaluated at t0, w0, which is equal to f evaluated at 0, 0.5, okay, which equals, so y is 0.5 minus t squared, or 0 squared, which is 0, plus 1, this equals 1.5. Okay. So S2 is equal to, so now we have T sub 0 plus half of H. So we evaluate F at, and now we'll write in 0.1. And it is W sub 0, which is 0.5, plus H over 2, or 0.1, times S1, which is 1.5. And so we are actually evaluating the function at 0.1. And so 0.5 plus 0.15 is 0.65. And so our function evaluates to, let's see, 0.65 minus 0.1 quantity squared plus 1. This equals 1.65, and then minus a 0.01, which is 1.64. And so S3, it turns out, we are evaluating F at 0.1, and if we compute W0 plus H over 2 S2, it turns out to be 0.664. And this evaluation of the function is 1.650. Okay. And S4, now we evaluate the function at 0.2, and W sub 0 plus H times S3 turns out to be 0.8308, and this turns out to be 1.7908. So we've computed S1, S2, S3, and S4. You see them here. Let me scroll up. And now we have to compute W sub I plus 1 given by this formula here. So W sub I plus 1 or this should be W sub 1. So W sub 1 equals W sub 0, which is 0.5, plus an H over 6. So in this case, H is 0.2 divided by 6, and then times S1, which is 1.5, plus 2 times S2, which is 1.64, plus 2 times 1.654, and then plus S3, or I'm sorry, S4, which is 1.7908. Okay. And if we evaluate, this turns out to be 0.82929. .33. Okay, so now to compare the exact solution. So y of 0.2, which in this case we're calling y sub 1, exact is 0.892986. Okay, I've made a mistake here. It's 0.8292986. So to compute error, in this case, the error is w sub 1 minus y sub 1, which equals, in absolute value, 0.0000053. So this is a pretty small error considering we have a step size of 0.2. If you recall using a step size of 0.2 for Euler's method, our error was much bigger. And for the explicit trapezoid method, it would be too big as well. So now to try to compare, do somewhat of an apples to apples comparison, let's consider approximating y of 0.2 with, in one case, Euler's method with a step size of 0.025, explicit trapezoid method with h equals 0.05, and Runge-Kutta fourth order method so we'll use Runge-Kutta fourth order method with h equals 0.1. And the thinking for using these different step sizes is this. If you recall, Runge-Kutta fourth order has 4 function evaluations per step, so there's 4 times as much work as Euler's method. So to try to make a comparison, an apples to apples comparison between Runge-Kutta fourth order and Euler's method, if we cut the step size by a fourth, the Euler's method under this scenario with h equals 0.025 and Runge-Kutta method using a step size of 0.1, we're doing 4 function evaluations for Euler's method to arrive at y of 0.1. So in this case, we're doing an apples to apples comparison. So if we do this, if we apply these 3 different techniques, numerical techniques, to the given initial value problem, let's see what we get for, we've seen what we get for RK4. Let's see what we get for Euler's method. So for Euler's method, we get an approximation of 0.82533385 is our approximation of y of 0.2. Trapezoid method, the approximation is 0.8290778. This is an approximation of y of 0.2. As we've just seen, Runge-Kutta fourth order. Well, actually, we didn't just see it, but if we use Runge-Kutta fourth order, the approximation is 0.829293. This is an approximation of y of 0.2. What was the exact? Well, if you recall, exact is 0.8292986. 0.86. So of these three methods, which is more efficient? Okay, we are comparing apples to apples here. We've done the same number of function evaluations in each of these three methods, and just from this, these figures here, clearly Runge-Kutta fourth order is the preferred method. So conclusion, Runge-Kutta fourth order is more efficient than Euler's method and the explicit trapezoid method. And this is based on the fact that the Runge-Kutta fourth order method is a fourth order method, that is, the error is proportional to h to the fourth power. And as I said, we will be discussing error for these different methods in class.